Friday. Today we're going to start what we call inverse functions. We're going to spend 2 days on them. So we're going to spend today and Friday. So they sort of go together like peanut butter and jelly. So try not to miss Friday's class if possible, because it really comes together on Friday, all of the whole package. Most teachers would do inverse functions all in one day, but we spread it out a little bit because it's an important topic for the rest of your math education here, and if you go on further to understand what inverse functions are. Okay, so EPRs were sent out yesterday, and EPR stands for Early Progress Report. And I have an obligation to let students and their advisors know if they're in danger of not passing the course at midterm, or if they're getting a D at midterm, there's a danger that you won't pass the course. So these went out for the people who had averages below 70. If you have a C or a C minus, the EPRs are optional. I don't send them out for people with C's or C minuses, just D's or F's. Now remember, in this class, an F is below 63 in average. Now, on most of those, I just said, contact me as soon as possible. And also maybe do peer tutoring and math studio hours or whatever. But if you get one of these, I would really appreciate you coming to see me so that we can maybe sit down and look at your schedule, how many hours you have a week. Are you getting tutoring? Can you see me at any point during the week? Just try to figure out something that will work a little bit better for you and how it's been working so far. For some of you, it's just, some of you have told me, oh, I just need to study a little more or do more homework or whatever. Some of you already know what you need to do, but it would be good just to touch base so that we can make a decision. I think you can withdraw from a course at GCC with a W up till November, I want to say like 4th or 8th or something like that. So we will have another exam before that date. So after the first 2 exams, we're 2/3 of the way through the semester. I think that would be a great time to use that as some type of decision point. And what I've told people in the past is, if you want to withdraw from the course, still stay in the course. People will still stay the rest of the semester and try to absorb as much as they can the first time through, and then they take it again the second semester. So that's another option. If you've got like 4 courses and they're all 4 credits, or you're carrying a heavy load and you're working outside 20 hours a week or whatever, it's tough. So sometimes you've just got to make decisions to make your life a little more manageable. And those are the kinds of things we can talk about on an individual basis that I can't talk with you in class about. Okay, so if you happen to see one of these pop up in your email, I guess that's how they're sent to you, or your advisor contacts you or whatever, then don't get freaked out. It's just something I have to do, and it's good information for you. And make an appointment to see me. Okay. All right. Any questions on any of this before we head on to today's inverse function idea? Where's your buddy? They're not, huh? Okay. Well, I'll come up and help you out there. All right. So today we're going to start with inverse functions. And we're going to start with a little bit of a review of what a function is and what a relation is. So you want to start us off, Shane?
The table shows the female literacy rate as a percent of adult number.
Okay. So of course, this table was much longer. I just chose 6 nations. And so you can see here that we're going to use this information to define a function. And the function is going to be, the domain of the function is going to be the 6 countries that you see in the table. That's your input. And then the range of this function is going to be the literacy rate. So if we were to describe this function, we would say this function is the set of all ordered pairs, these 6 ordered pairs, where the first component or the input value is the actual name of the country, and then the second component or the output is the female literacy rate. So we're calling this a function because if I look at my table and I look for Brazil, I see that there's one value and only one value for the output. I'm not confused at all. So the idea that we're going to work on today is this idea of undoing a function. And one of the ways you undo a function, we're going to look at several ways of undoing it, what this idea of undoing means. One way to do it is just to switch the order of the inputs and the outputs. We're going to switch the order of the domain and the range. So if we do that, if we interchange the domain and range, what we're doing is we're undoing this function, okay? And we get this new set. So now the question is this new set of ordered pairs, is the new set of ordered pairs a function? So I want you to look those over and tell me if for each input there's one and only one output. Someone said no. Who said no? Shane, right. So Shane notices that if you're the 0.99, where do you go? Notice 99 goes to Germany, and it also goes to Japan, right? So once we interchange the domain and range, the resulting does not produce a function. And do you remember what it's called when it's just a set of ordered pairs, when it's not a function, what the name is? We're going back a couple weeks now when something's not a function. Give me an R. A relation, right? No, it's a relation. So remember, a relation is any set of ordered pairs. All relations are all functions are relations, but not vice versa. Okay. So in this particular case, when I interchange them, I got a relation. So that's just a little review. I know it was a while back, so I wanted to throw that in at the beginning of today. Okay, so if a function f is a set of ordered pairs, x, y, we could call it, another way we could refer to that is x comma f of x, okay? Then the changes produced by f can be undone by reversing the components of the ordered pairs. So the resulting relation, and it's fine to call it relation because even if the result is a function, it's still a relation. So the resulting relation, when you switch them around, may or may not be a function. So let's look at the undoing of functions today and their properties. In fact, we're going to be looking at these properties for 2 classes. Mary, I know in case it gets loud, but it's really too hot in here for me. Do you mind opening the door? Thank you. All right, so here's our first relationship that we're going to look at, and it looks like it's a function because f of t is 6 plus 2t. That's a linear function, right? And we know all straight lines except for vertical lines are functions because for every input you have an output. So in this particular case, our input is t days, and our output is called the height in inches. Okay, so that's what my ordered pair looks like. You can also write it like this: t days and f of t is your output, which is measured in inches. So h is equal to f of t. So where you see h, you could also say f of t. The height depends on the number of days that this corn seedling has been planted. Okay. Now notice it says my domain is very specific. It starts at 0 and it ends at 3. So I'm only looking at the height of the corn seedling over 0 days, 1 day, 2 days, and 3 days. So if you were graphing this, all you would need is the right-hand quadrant of your graph, and you would begin your function at 0, and you would end it at 0 some number, and then 3 some number. So let's fill in this table according to this equation up here. So if t is 0, I find the height, which is f of 0, by plugging 0 in where I see t. So I get 6 plus 2 times 0, which is 6. So that's your coordinate, right? Your y-intercept, your h-intercept in this case. This is h, this is t. So 0, 6, there I am. Now, some of you may remember that from your linear function, once you know your starting point, you know you're starting at 0, 6. You can use your slope, which is right here, 2. It says I change 2 inches for every day that goes by. You can then just add 2 to all your answers here. At 1, you're going to grow 2 more inches a day later, so your answer is going to be 8, then 10, and then 12. So as you see here, the change is 2 to 1. The rate of change is 2 to 1. It's constant when you have a straight line. So this is a straight line that looks like that, and your last ordered pair here would be 312. So that's what that particular function looks like over that domain. You can also represent that function by writing a set of ordered pairs, which is what we started to do here. When t is 0, h is 6. When t is 1, we're 8. T is 2, we're 10. And 3, we're 12. It's another way to represent that function. So look, we got 3 different ways here, actually 4. Let's look at all 4 of them. You've got a graphical representation here. This is what we call a graphical representation of the function. We've got a symbolic representation here. Symbolic is like an equation. We have a tabular representation there. And then we have a numeric representation with the ordered pairs. Okay, so there's that function. You know, it's not that exciting, right? I mean, it's just four ordered pairs. But suppose now I asked you, here's our function, h equals 6 plus 2t. Notice this function is solved for h. And what does it mean when we solve something for h? It usually means we input a t value and out pops an h value, right? So now let's look at this question. Suppose I wanted to know how many days it would take for the height of the seedling to reach 36 inches. How would I find that answer? What would I do at this point, given this information? I want to know when the height is 36 inches. So what would I do mathematically to find that answer? 36 equals 6 plus 2t. So what Shane said is he's going to take 36, and where he sees h, he replaces that with 36. Okay? So now what you want to do is you want to solve this equation, solve for t. Okay? So everything that happened to t is now going to be undone. That's what you do when you solve a linear equation. Because what happened to t here? T was doubled, and then 6 was added to that result. Now to get t, we got to undo it. So here we're starting. So here's where our starting point is. Start with 36, and we want to get to t. Okay, we want to get to a value with t. So let's see how we do that. Well, what would you do here to solve this equation for t? What would be the first thing you would do, other than Shane? Subtract 6. Okay. All right, so I'm going to do that over here, subtract 6. Okay, I'm just going to write it over here as well. All right. So we get 30 here, and we get 2t here. We subtracted 6 from both sides of the equation. Then what would I do as my final step, Haley? Divide both sides by 2. So see, when I write 30 over here, I've combined like constants. So here, 36 take away 6, I'm leaving it like that. But for us to think of it as a single quantity, I put my parentheses around it, and there's my 2. And so t is 15. So this is how I would get t. I subtract 6 from 36, and then I divide that result, the whole thing, by 2, and I get 15. So we get 15. So now I input h, my height, and out pops the number of days. So as you can see, by solving this equation for t, I've undone everything that's happened to t. And now I've totally switched my output and my input. So now if you tell me my height, I can tell you my time by solving the original function that was solved for h by using a little bit of algebra on it, solving the linear equation now for t. So in this equation, h is the input and t is the output. We've interchanged their roles. So in general, what we just did is we started off with a height right here. We subtracted 6 from it, and we divided it by 2. This is now a new function, because now what I've done is I've inputted a height. Here's my input. The input is the height of the seedling in inches. And the output is this whole thing. The output is G of H or T or this expression, H take away 6 over 2. These all represent the output. So let's create a new table of values for this new function called G of H. So let's see, we've got 6, 8, 10, and 12 here for my inputs. Do we have to do much work to get the outputs here? How do I get the outputs for 6, 8, 10, and 12? What would you do to get these outputs? Any idea? What'd you say? Okay, so I find G of 6, which is H, which is 6, take away 6 divided by 2, which is what? 0. Okay, so my first ordered pair for this function is 6, comma 0. So I go down there and I fill that little ordered pair in. Okay, what about 8? What's 8 going to be? Has anybody got the output right now for 8? 1. Okay, 8 take away 6 is 2. Divide 2 by 2, you get 1. So when the height is 8, I've been in the ground for 1 day. And when my height is 10, 2 days. And then when my height is 12, 3 days. So this is the set of ordered pairs HT over the domain 612. So in my first class, someone said, wait a minute, why is the domain 612? Someone in my first class asked, why is the domain 612? So what would your answer to that be? Why is the domain 612 here? 6, comma 12. Right, they're the inputs, right? Our independent variable here are our inputs, the same thing, is H, the height, and it goes from 6 to 12. That's my domain. If you look at your ordered pairs, you have 4 input values, and that's it. Mary? Yeah. This was just a totally separate question here. In fact, I've already thought of when I asked you, how would you find the height of 36? That wasn't in the original domain. So I was actually, when I did this, I said I should pick something that's in this original domain or the range in this case. I was just doing that so we could practice the undoing. But you're right. You wouldn't see 36 over here because it's not one of the values that came out of here. So that's a good thing to notice. Okay. So what I want you to do now is I want you to look at the first table in your first function and the second table in the second function. One of those functions is called F. One of those functions is called G. And just write down anything you notice about them. Okay? Anything at all that you notice. And then we'll record some of those observations in a few minutes. Let's write down some of the observations. So anybody got one that they noticed between these two functions, Mary? The H and T values are always together. Okay, so right. So with the F function, we had 0, 6, 1, 8, 2, 10, 3, 12. And what Mary noticed is that when you went to the G function, if 0 and 6 were together, they were together in the ordered pair with G. But what's the difference, Mary? They switch places, right? Positions, right? So she noticed that if you were together, if you were one of these inputs and outputs in your first function, you stayed with your input and output, except for now you just switched your place, your role. Okay, what else did you notice? How else could you say that in another way using other terminology that we've learned in the class? Anybody got a different way to say sort of the same observation that Mary noticed? Okay. So what Buddha is saying is that let's look at the range of f. What does the range of f look like? If you go back to your first function, what interval would you use to describe the range of f? Describe the range of f of your first function using interval notation. Adam, what would it be? Need something else. Brackets, right. Okay. So Buddha noticed that the range of f is exactly the same as the domain of G. Wow. Cool. So the domain of G is 6, 12. Anybody else notice anything else? The range of f is the domain of G. You can do one more sentence like that. Say that again. The domain of f is the output of G. Or in other words, the range, let's keep it in the same format. The range of G is 0 to 3. And it's the same as the domain of f. Right. And that's exactly what Mary noticed, except for it's just observed in a different way. It's the only difference. The language is different, the ideas are the same. All right, so we've got this kind of funny kind of like interchange going on, okay, with these particular functions. Okay, so let's continue this idea a little bit further. So we call these two functions, now we're going to use the same input variable x. If you see a function f of x equals 6 plus 2x, and then you see a function g of x, x take away 6 divided by 2, we're going to call these functions inverse functions. And the reason that they're called inverse functions is exactly for the reason that we call them inverse functions is one of the observations you just made, that the range of this function f is the domain of the function g, and the range of g is the domain of f. Anytime you have that situation going on, you have inverse functions. That's one way of telling that you have an inverse function. We're going to look at several different ways of telling whether you have an inverse function or not. Okay, but this is one of the first ways. It's by this interchange, this role change. Okay, we're interchanging roles here. But we come up with a new symbol to denote that one function is the inverse function of the other. We can keep saying f and g are inverses, f and g are inverses, but as you know, mathematicians like to come up with symbols that are universal, so that regardless of what language you speak, you understand the symbol. You may not understand the word inverse in English, but if you see f to the -1 power, you know that when you see that -1, it's not a power. I called it a power, but it's not acting like 3 to the -1. If you see 3 to the -1, you know that's defined as 1 over 3. But that's not what you do when you have a function there. It just is read the inverse of f, or f inverse. Okay, so that's what that little -1 means. So now we're just going to rewrite g of x. We're going to use this notation to say, hey, g of x is the inverse of f. Or you could do this. You could say, hey, let g of x be your big function, and then its inverse is 6 plus 2x. Doesn't matter. They're both inverses of each other. Okay, you can either say g is the inverse of f, or f is the inverse of g. Doesn't matter how you say it. Okay, so now let's take a look at the same idea with this functional notation. Here's our same two functions we just looked at, but now instead of calling calling the second function g of f, I'm saying it's the inverse of f. So how would we evaluate f of 10? 26, right. I take my original function. So now we're not doing the height of the seedlings anymore. The domain and range of these functions are all real numbers, okay? So it's just a linear function here, And this is also a linear function. This is the same thing as 1/2 x take away 3. So they're both linear functions. So there's no restrictions on our domains or our ranges. So f of 10 is 6 plus 2 times 10, which is 26. Okay? That's so the input is 10, the output is 26 with the function f. All right? Now let's take a look at f inverse. So f inverse, I'm now taking this output and I'm putting it in as my domain, and let's see what happens. 26 take away 6 divided by 2 is 20 divided by 2 is 10. Acts just like you think it should act. You're right back to where you started. Notice, I started with 10. I put 10 into my F machine. Out came F of 10, which we call 26. That went into my G machine, my F inverse machine, and out came F inverse of 26, which we call 10. You're right back to where you started. You did a round trip. It's a round trip. Sometimes you might feel like in math you're right back to where you started, but you do make progress. Sometimes it doesn't feel like it, but you do. So this is like kind of a neat thing that happens with inverse functions. And what we just saw only happens with inverse functions. Okay? It only happens with inverse functions. That when you put the two functions together, does anybody know what we call this when we put the two functions together in sequence in like tandem, what we gave, the name we gave to those kinds of functions? We put the output of one function in the input of another function. No, it was a couple classes ago. Usually that class comes right before inverses, but we had that after class 16. Anybody remember the name for those functions? Has this little symbol here from class 20. So give me a C, give me an O, give me an M, give me a P. Composite, right? These are composite functions. When you compose these two functions, you take the output of one function, you put it into the input of the other. When you compose functions in this way and you get right back to where you started, you have inverse functions. And it only happens with inverse functions. So this idea right here, B and C, if you have some way of highlighting this in your notes right here, this idea is a really big idea. Really big idea. And we'll continue to work on that in just a minute. Let's compose these two functions. Let's compose them and let's actually change the order. And if you recall, when you have composite functions, any composite functions, f of g of x, remember the order mattered. If we compose two functions and then we change the order of the composition, they were not equal. And I said in general, there's going to be a special case, an exception, and that's what we're going to look at today. So let's go back up here and let's compose these two functions. Let's take a look at f, and instead of calling it f of g of x, we're going to say f composed with its inverse. So this means the input now is my inverse function, and everywhere in my f function where I see an x, I'm going to replace x with f inverse of x. So instead of 6 plus 2x, my input now is all this green stuff right here. Here's my input. This is my input into my f function. So here I am. So that's what that composition means. Now I want to replace f inverse of x with what that means. What is f inverse of x? F inverse of x is x minus 6 divided by 2. So let's simplify this. Let's simplify it. So the 2's cancel, and we get 6 plus x minus 6, which equals x. So when I compose F with its inverse, I come right back to X. We just did that a minute ago. That shouldn't be a big surprise. We just did it up here. We composed these two functions in this machine. But what if I reverse the order? Will I get the same thing? So let's try it. F inverse of f of x. So now I look at my outside function. My outside function is my inverse function. So I focus all my attention up here on my inverse function. My inverse function says to take my input, subtract 6 from it, and divide it by 2. What's my input? Here's my input. My input is f of x. So I replace input with f of x. I subtract 6 from it and divide it by 2. And now I replace f of x with what f of x equals, which is 6 plus 2x. I subtract 6, divide by 2. I get 2x over 2. I'm right back to where I started with x. So this is the really big idea. The really big idea says it doesn't matter the order that you compose a function with its inverse. You always come back with the value you start with. I started with x here. I composed my functions. I ended up right back where I started. If I reverse the order of that composition, guess what? I wind up right back where I started. So this is only true. Hey, Ted. Oh, yeah, sure. It's all right. Only true for inverse functions. It's the only time you will see that when you change the order of your composition, you get the same result. So that's what you should have in big capital letters somewhere in your notes. This is, and it's so important that this is actually how we define inverse functions. Okay, this is actually how we define it. So I'm going to skip the next little thing real quick and go to 6. Now this didn't all come out on my mind, but it's all on your lecture notes. So let's take a look at this definition. So if f and g are two functions, and you're not sure yet about f and g and what their roles are, or if they are inverses, one way to verify, so this is how you verify, this is how you verify that two functions are inverses of each other. So if on your quiz next week, I say to you on Monday, here's f, here's g, verify that these two are inverses of each other, this is what you would do. You would compose them, change the order of the composition, and if you come back with the variable x, your input, then they're inverses of each other. So for example, let me give you another example. Here's f of x. I'm just going to say 3x plus 4. Here's g of x. If I gave you this on Monday on the quiz and I said, verify that f and g are inverses of each other, you'd say, okay, if they're inverses, then f of g of x has to equal g of f of x, and they both must equal x. So you check them out. So you say, okay, I'm going to go to my f function, and where I see my input, I'm going to write g of x. I'm going to go to my g function, and where I see my input, I'm going to write f of x. And both of these must equal x, or they're not inverses. So let's see, 3 times g of x. G of x was x take away 4 over 3. Then I add 4 to the whole thing. The 3's cancel. I get x minus 4 plus 4. That equals x. Bingo. Then you try the next one. F of x is 3x plus 4 minus 4 over 3. 3x over 3. That equals x. Bingo. Now you know these two functions are inverses, and you could now call this f inverse of x, or vice versa. You could call this one g inverse. Doesn't matter which one you pick on. All right? So if you're ever asked to verify that two functions are inverses, You do the composition of the functions, then you reverse the composition, and if they both come back to X, you're golden. Okay, that's how you verify. And remember that what we just talked about, that the domains and ranges interchange, and that's what this final piece is here that didn't come out on the Smart Notebook page. So let's go back here to this number 5 now. So this is all the information we just had a minute ago, but it's put in tabular form. A minute ago we had it in ordered pair form, and it looked like this. We just had a bunch of ordered pairs. Okay, but now it's in tabular, so it's 1, 8, 2, 10, 3, 12, 4, 14, blah, blah, blah. Okay, so if I tell you that you have a function and its inverse, and I give you the table for the first function, you can automatically fill out the table for your inverse function by knowing that the roles of the input and output exchange, the domain and range. So you look here, here's the output for your function f. Where does that go in this table? Where does that go in the second table? It becomes the input, right? It becomes all the x values. So 8, 10, 12, 14, 16. And once I perform my inverse on these, where do I end up? What are my final values here for those 5 values, those 5 input values? Right where I started, 1, 2, 3, 4, 5, right? So inverse functions swap the input and the output. The domain of f is the range of f inverse. The range of f is the domain of f inverse. Okay, so you should try writing that out on your own to make sure you can keep them straight. What a lot of students like to do is they like to sort of think of like pictures, and they have an input here, let's call that A, and they have an output here, and they call this F, they call this F inverse, and they write this, F of A equals B. So I perform the function F on A, and it takes me to B. Then I take the inverse of B, and guess what? It brings me right back to A. That's another way to represent these ideas we've been talking about, whether they're in ordered pair form, whether we're talking about domains and ranges, or whether we use this notation. This is the definition of what inverse functions do as well. Okay? So what we're going to spend like 20 minutes on today, you're going to spend 20 minutes on, is how do you interpret functions and inverse functions? It's important that you can look at a given paragraph and understand what an inverse function does, given a particular set of inputs and outputs. So I'm going to give you some strategies here in A, B, and C. You're going to see something different in your group activities, but employ these strategies when you get to your group activity. These will be helpful to you. And I told my first class, the problems that you see, A, B, and C, you will see a problem like this on your final exam, guaranteed. You will see a problem like this on your quiz. You will see a problem like this on your test. So if you want to know right now, like 6, 8, 10 points, I don't know how much it will be on your next assessment, just circle this and say, make sure you study this for the next quiz, for the next test, and then when the final comes around, because I will be asking you how to interpret functions. So let's take a look at this. And one of the ways that you want to look at functions and their inverses is to identify what your inputs are and your outputs for each one. So let's say P, capital P, is equal to F of T. This gives the population. So F of T, or P, gives the population of Greenfield. So that is my output. So my output is the population P of Greenfield, and my units is number of people. It's not thousands of people, it's number of people. That's my output. Notice, what is my input? My input is this little letter here called T. That's my input. So now I look for where T is defined in my sentence, and I go over here. T is the time in years, and this is my unit, in years since 1900. Okay. All right, so if that's my function, what would, even though I didn't ask you to do it, on the side, you should do this. You should say, okay, what would be the input and the output of my inverse function? Okay, so off on the side, what would be the input and output of the inverse function? So could someone help me out with this? What would be the input of my inverse function? The population, right? Because I take the output of my first function and that becomes the input. Notice I'm keeping the colors the same. So the input is the population, P, number of people, blah, blah, blah. And then the output of my inverse function would be time, T, in years since 1900. So then when I give you something like this and I ask you to write a sentence explaining what it means, if you have your little inputs and outputs off on the side of your paper, all you have to do is look at it. So you say, okay, what is the input of my inverse function? The input is the output of my first function, F, or which means it's the population. So this is the population of Greenfield. That's what that is. That's my input. This whole entire thing, F inverse of 1400 is equal to 57. So that symbol and the number 57 represent the output, which is 1957. It's 57 years after 1900 because I've switched roles. So if I ask what this means, I would say that this function, this tells us that in 1957, the population of Greenfield, I'm going to actually reverse that. This tells us that the population of Greenfield, doesn't really matter, of Greenfield was 1,400 people. Notice my unit with my number, specific units in 1957. So in general, what does the inverse function represent? And this is really tough for students to get. What does the inverse function represent? Notice what the output of your inverse function is. It's time, the number of years after 1900. So always look at your output. So your inverse function represents the number of years since 1900 for a given, because that's what you're given, it's your input, for a given population of Greenfield. So how do I write the sentence for my inverse population? I look at my output. The output is the number of years given my input. That's how you can set up all of your sentences to represent your inverse function. So let's try one more together. I'm going to rely on you for help now, okay? So here's a new function, brand new function. Want to read this for us, Ben?
C is equal to F cubed. Fix the cost in dollars. Q lunchboxes. What are its inputs/outputs?
Okay, so let's look at the function f first. Okay, and let's figure out what the inputs are for f. Let's figure out what the outputs are. In words, with the units, right? So what goes into our f function? Can you help us with that, Austin? What goes into the f function? So what, well, let's see, what is the little letter inside the parentheses?
Q.
Q, so that's your input. And so what does that represent? Right, so, right, so Q is what? Number of lunch boxes, right, number of lunch boxes, okay? The outputs are represented by this whole thing, F of Q, that's your output. Or it's also equivalent to this letter called C. And then you read the first part of your first sentence, and it tells you what C and F of Q represents. What does that represent as the output? Honey? Right, the cost in dollars to manufacture Q boxes. Okay. So that's my function F. And if you wanted, you could represent it like this, Q lunch boxes. You could represent your little ordered pairs, and C dollars. You could also represent it as Q, comma, F of Q. Whatever works for you. Now we know something's going to happen. They're going to switch roles in your inverse function. So my inputs and my outputs change place. So if I'm looking at my inverse function, what goes in is the cost in dollars. And what comes out of that function is Q, the number of lunch boxes manufactured. If you have that information written down for yourself to help you, it's really hard to get this mixed up. If you don't take the time to do that for yourself when you're first learning this, you can get mixed up really easily. So I'm showing you a strategy of how to answer these questions. Okay, so when you read about a function and it's defining the input and the output, do this type of little scenario for yourself. First do it for the function, and then reverse the roles for your inverse function. And that's really going to help you when you come to a question like this. What does F inverse of 200 equal 40 mean? So you say, oh God, I can't remember. I'll go back up and look. I'm in my inverse function. What is my input here? My input is the number 200. My output is 40. As an ordered pair, this is what it looks like. What is the input into my inverse function? Oh, right, it's the cost. What's the output? The number of lunch boxes. So if I have to write a sentence for this, I can say it costs $200 to produce or manufacture 40 lunch boxes. Boom. That's how I interpret it or explain that notation. Any questions on that? Okay, what does F inverse represent? Yep, Mary. There really isn't. I like when I look at this, I just like read it straight across. I just say it costs to get this. It costs 200 to get that. When I write this sentence, I say, what does the inverse function represent? The inverse function represents how to calculate the number of lunch boxes given a particular cost. So I look at the end result. So my inverse function tells me how to calculate what? The output. So here's a sentence you could use. Calculate the output given the input. So you could, if you want like a little prescription, that's one way of writing what the inverse function represents. So it calculates, the inverse function is going to calculate some value for you. The value it's going to calculate is the number of lunch boxes manufactured for a given cost in dollars. So that's just a little thing. If you like having like little recipes, that helps you understand how to write things, because this can be really confusing. That's fine. So up here, you could have said that this sentence means that, you're not calculating now. You actually have the information here, Mary. So the difference between the two is this is a very specific point in your function, inverse function. This is a general, what does my inverse function represent in general? So my inverse function represents my ability to calculate how many lunch boxes I can make if you tell me how much money I got. If you give me the money, I can calculate for you the number of lunch boxes. The other way around, my F function tells me the cost in dollars. It's going to calculate the cost if you tell me how many lunch boxes you want to make. And that's what we all do, right? When we go online and we buy stuff, we can figure out our cost of shipping and handling if you have a certain quantity you want to produce, you want to buy, right? So it just depends on which function you're looking at. Now you have C to practice on your own. Try C, and then let me check it for you. And then I'd like you to work on your activity for today, which it's very kind of an interesting little thing. It's called columns and cell phones. So you'll have about 20 minutes to work on that. So please let me check C before you move on, or at least one person at the table, and then you can all check together however you want to do it.